everyone, welcome back. In this video, we will look into the different types of functional groups in organic chemistry that are very common, as well as different ways to represent organic molecules. So, when we study OChem, there are patterns. So, we group compounds together based on their structure-property relationships. And some common families of organic groups are called functional groups. And basically, a functional group is a characteristic atom or group of atoms that are inserted into a hydrocarbon. And so it's really important that we're able to do this, that we're able to come up with patterns and functional groups, because as I said in the previous video, there are millions of organic molecules out there. And so it's important for us when we see something that's a new organic molecule we haven't worked with, that we recognize some of the structure, patterns, and their properties so that we can make an educated guess as to how that specific organic molecule will react. So that's kind of the purpose of this particular video here, is to introduce you to those common patterns, those functional groups. And so it's really important that you learn these functional groups in order to learn the language of OChem. So the first common functional group are alcohols. And alcohols are characteristic of that OH. Now, OH here, right, we refer to as the alcohol group. In biochemistry or biology classes, you may refer to it as a hydroxy group. Same thing. Also, in addition, R stands for the rest of the molecule, which is largely composed of carbons and hydrogens, and that's why I refer to a hydrocarbon here. Hydrocarbon meaning a chain of carbon atoms with hydrogens attached. And so anytime you see R in organic chemistry, it just refers to the rest of the molecule. Okay. Now we can also represent the formula as a condensed form, where we just don't include the lines in there, the bonds. And an example here is ethanol. Right, we see the alcohol here, and the CH3CH2 is the hydrocarbon, right? It's commonly known as ethanol, or it can also be named as ethyl alcohol. Ethers have an oxygen that is bonded to two R groups. Now, the R groups don't necessarily have to be the same. So sometimes if the R groups are different, that would be asymmetrical. And we would refer to this R over here as R prime, for example, just to distinguish it from this R on the left side here. However, a lot of ethers are symmetrical. So the example given here has two methyl groups attached on either side of this oxygen, and this one's referred to as dimethyl ether. But I just want to emphasize that it's not necessarily asymmetrical ether. You could have two different R groups. Then there are the aldehydes, and aldehydes have a carbon double bonded oxygen, and on one side of the carbon is a hydrogen, and on the other side is the rest of the molecule. Now, be mindful, sometimes it's shown in condensed form, which can be a little confusing for students when they see the CHO. Sometimes students will see this and think, ooh, alcohol, but the order is reversed. CHO indicates that it is an aldehyde, not an alcohol. In this example here, we have acetaldehyde, right? So you have the R group is just that methyl group, and then the aldehyde part of it. And the difference in naming it between an alcohol and aldehyde is a little subtle here. You can see it's ethanol for alcohol and ethanol for aldehyde. You can see here this is a ketone. It has a carbon double bonded oxygen, but instead of a hydrogen on one side, each side has an R group. Once again, most ketones are actually not symmetrical, so I'd like to put R prime here, just so you know it doesn't have to be a symmetrical ketone. In this case here, it is when we see acetone here. It's a very common cleaning solvent that we use in organic chemistry, as well as a great fingernail polish remover. And the name for this particular molecule, besides acetone, which is the common name, but it is propanone. So O-N-E for the ketone. Carboxylic acids have carbon double bonded oxygen, but on one side is an OH and on the other side is the rest of the molecule. Its condensed formula is COOH. As you see here, we have ethanoic acid, which is very commonly known as acetic acid. We have esters, which look a lot like carboxylic acids, but instead of an OH, it's an OR, so there's a rest of a molecule on that side as well as the left side. Once again, usually esters are not symmetrical, they are asymmetrical. And so a lot of times you would see a long chain hanging off on this side, but a methyl or ethyl group hanging off of the oxygen. And this is referred to as, in this example, methyl acetate. And then finally there are amines, which are nitrogen-containing molecules. So nitrogen can have R groups attached to it. It can have hydrogens. The R groups don't have to be the same. So you have R prime and R double prime here, for example. And the example they do show here is ethyl and then amine. And amines are derivatives of a molecule you may already be familiar with. They're derivatives of ammonia. And we will learn in future videos that amines are good bases, not necessarily strong bases, but they are good bases in organic chemistry. So once again, it's really important you learn the language of OCHEMs. So make sure you learn these functional groups. For me, I created flashcards, but I know that you can use a Quizlet, for example, online and find an app that can help you learn these functional groups. And this is not a totally comprehensive list. There are many other functional groups out there that we're not covering in this particular course. However, learning those other functional groups that you may come across in other textbooks or other online resources will only help you when you do take OCHEM in your future. All right, so let's do an example together. I'm going to use a highlighter, so I'm going to highlight and identify functional groups in warfarin, and this is medication that's used to treat blood clots. So go ahead, pause the video, and try on your own to identify the functional groups first, and then come back to the video to check your answer with me. All right, well, I hope you've had the opportunity to identify the functional groups in the molecule warfarin. Now, the first functional group that I found, this is alcohol here, the OH. All right, the next one you should find looks like we have a carbon double bonded oxygen. On one side of that carbon is the rest of the molecule, and on the other side is an oxygen, but the oxygen doesn't have a hydrogen attached to it. It has another R group. So what is this particular functional group called? Excellent. This is an ester. What's another functional group you found? Good. Found a ketone. Where we have a carbon double bonded oxygen and then 2 R groups attached to that particular carbon. This is called a ketone. I'm going to highlight some other things that weren't in the table but we've learned or we will learn in future videos as well. Double bonds are functional groups in and themselves, and we will learn them to be called alkenes. In addition, this ring here is an aromatic hydrocarbon, and it's referred to, and we have another one over here. These are referred to as arenes. They react differently than alkenes. The AR part stands for aromatic, right? And it appears they have double bonds in them, but we'll learn that all these bonds are of equal length. And so it's kind of a hybrid between a double and a single bond due to the resonance structures. So anyways, these are also kind of functional groups that you should be aware of and you should be able to identify as well. And they have their own class of reactions that you will learn if you take organic chemistry. Now, if you do take organic in your future, then the way it's structured is that we have nomenclature, which is naming, and that's what I will focus on in these videos here. I won't do all of naming. I won't teach you how to name esters or ketones or aldehydes. I'm going to mainly focus on alkanes, alkenes, alkynes, and aromatic hydrocarbons, but that will be a good foundation for naming other types of organic molecules in the future. You would also learn about these functional groups and their properties. So properties meaning boiling point, solubility is a big one, and we're going to discuss solubility in the future, safety, and definitely reactivity. In addition, you would learn how to synthesize those functional groups. You would learn about reactions of those functional groups. And you'd also learn how to characterize them. And what characterization means in science is that we use instrumentation to prove the identity of your compound. I always make the joke with my students that a lot of organic compounds are white powder. So you as a scientist have to prove to your peers or to the scientific community that you made the correct white powder you were designing, right? And that you synthesized in your laboratory. And so you have to go through a series of characterization techniques so that you can prove without a doubt that it is the correct product. And some characterization techniques include NMR. This is nuclear magnetic resonance spectroscopy, very powerful tool for identifying an organic molecule framework of carbons and hydrogens. You could also use an IR infrared, and that is used to determine the identity of functional groups that are present in your molecule, as well as if you have an aromatic structure, it can give you an idea of what substitution pattern may be taking place. You can also use ultraviolet, UV vis, spectroscopy to identify the absorption of your molecule. And then also mass spec, which can give you an idea of the total mass and the way your molecule fragments depending on which mass spec technique you would use. And you can imagine this is something that you would begin learning different instrumentation techniques in an organic chemistry class. But if you go on to become a chemistry major, there are classes, undergraduate and graduate classes, dedicated to studying these instrumentation techniques. And so if you, like I said, go on in your future and you take an organic class, you'll learn all about NMR, IR, UV, and mass spec and how powerful these tools can be. But I just want to reiterate that the talk I'm giving in these videos for this organic chemistry introduction is like a TED Talk. It's an overview of OChem. And you will immerse yourself if you do take organic chemistry in your future, and you will learn the language of OChem. But it's my goal in second semester general chemistry just to introduce you to some nomenclature and identifying functional groups so you can begin learning that language. It's very important that we learn how to draw structures properly. And so there are 3 different ways, and I will prefer the third way for you to draw your structures because that's the most common way in organic chemistry, and I am a trained organic chemist. But initially, you probably will feel more comfortable with structural formulas, and that's okay. And we did that in the previous video when I showed you some constitutional isomers. So what I mean by structural formula, everything is drawn. All the atoms. And so butane has 4 carbons. Each carbon needs 4 bonds. And so we fill in those hydrogens, we draw them out. And that's the structural formula for butane. And you can imagine that if you had a molecule like warfarin in a previous example we just worked identifying functional groups, that would take forever to draw that structural formula, right? There's a more condensed way to do it. It's called the condensed structural formula, where you start to group atoms together. But once again, this is not the most efficient way to draw our molecules. It's not as commonly used. However, it's really important that you're able to read condensed structural formulas and then be able to kind of transfer them to what the actual molecule would look like. The most common way is skeletal formulas, and the way it would look like for butane is as such. Okay? And initially, I remember as a student that I would look at these and I'm like, what is going on here? And it just took some practice to understand, okay, when I read these structures, this is how many carbons are present. This is how many hydrogens are present. So let's go through those rules together. Now, every bond represents a carbon. So you saw that zigzag line that I drew here. Every bond represents a carbon. So for example, with butane that I just drew for you, this is carbon 1, 2, 3, 4. And I love to number my carbon chains. So if you have different color pens available, then utilize that. A lot of organic chemistry is very visual. And when I teach organic chemistry, I always use different colored pens so that it really stands out which carbon we're referring to, or where is the new bond formed between which 2 carbons. So it's a very useful tool to have. All right, so we do not draw hydrogens attached to carbons. It's going to save us a lot of time, right? We mentally supply them knowing that carbon always needs 4 bonds. 4 bonds and 4 bonds only. So for example here, I know that this carbon here, carbon 1, only is attached to one other carbon. So how many hydrogens does it have left? It needs 1, 2, and 3. Carbon 2 has 2 bonds, so it needs how many hydrogens? Good, 2. 1 and 2. Carbon 3 needs 2. And carbon 4 needs 1, 2, 3. So you're just always adding up to 4 when you're mentally supplying all those hydrogens that are attached to your carbons. The third rule for drawing skeletal structures is that you want to draw other atoms like oxygen, nitrogen, and any hydrogens attached to those atoms. So for example, let's draw an amine. And so you can see here that we have our carbons and there's hydrogens attached, but once we run into nitrogen, we have to write out that nitrogen, otherwise it'll be assumed to be a carbon. And we need to attach any hydrogens to that specific nitrogen. Those are drawn out here. And so the molecular formula for propylamine is what I've drawn here, is C4, or actually butylamine, because it's 1, 2, 3, 4, butylamine, C4, H11N. We can count those hydrogens to make sure they add up correctly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And if initially while you're learning how to draw structures, it's okay to draw in the hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And it's important that you're able to read skeletal structures so that you get the correct molecular formula as well as the correct molar mass if you're doing some type of stoichiometry calculation, like calculating percent yield. All right, let's practice. So we want to draw the structural formulas and the skeletal formulas for the 3 constitutional isomers of pentane. And in this example here, actually, I'm going to focus mainly on the skeletal formulas to save space and some time. You can later on, as extra practice, transferring the skeletal formulas into structural formulas is added practice. Now, pentane has the formula C5H12. And so I always draw the straight chain first. So 1, 2, 3, 4, 5. Remember that constitutional isomers have the same molecular formula, but different atom-to-atom attachments. And so a trick I always teach students is when you're asked to draw constitutional isomers of these alkanes is that once you've drawn the straight chain, there's no other way to draw 5 carbons long. We have to now draw 4 carbons long, but with a branch, so that it adds up to 5. So that's why I think the skeletal structures are a little easier to read. It's easier to visualize if they look different from a previous structure you've already drawn. So I'm drawing the 4 carbon series, and in order to get 5 carbons, I need to branch one off. I need to add like a methyl group, for example, and I'll go into naming in the next video. And so here we have 1, 2, 3, 4 carbons. And we will learn in the next video that the name of this particular organic molecule is 2-methyl-butane. And then we're going to draw another one. 3 series, so 3 carbons long, but with 2 branches. So this is 1, 2, 3. And this one is 2,2-dimethyl-propane. So when you're drawing constitutional isomers, it takes a bit of trial and error. It takes some practice. And sometimes students will ask me, okay, well, why couldn't we have drawn this one here? Well, what we're going to learn is when we start naming these compounds, we're always going to number so that the branches get the lowest number. So this one you would number from right to left. 1, 2, 3, 4. And so the name of this molecule is also 2-methyl-butane. Which is the same as what we've already drawn. It's not a different constitutional isomer. It's just the same one, but rotated. Okay, so that's why it's going to be very important for you in the next video to really master naming your compounds, so that if you're asked to draw constitutional isomers and, different constitutional isomers, then you should also name them to make sure that they each have different names from one another. If they have different names, then they are constitutional isomers as long as they have the same molecular formula. So once again, pentane, 2-methylbutane, and 2,2-dimethylpropane are the 3 constitutional isomers of pentane C5H12. Thank you for watching, and see you next time.